A pulse width modulated signal is just a square wave signal that has different duty cycles. Before we jump into designing digital circuits that generate such signals, we need to talk about a couple of main characteristics for such signals. The first of which is actually the switching frequency. Your system operates at a very specific frequency, and we're going to call it the system frequency. The switching frequency is a completely different frequency, and it's the frequency of the actual square wave that your circuit should generate. Okay? Regardless of the duty cycle, you still have a frequency for this particular square wave. Why do we care about the frequency of the pulse width modulated signal? Well, as it turns out, if you connect this particular signal to an analog device, let's say an LED, this particular device will definitely see the zeros and ones. However, it is an analog device, so it does not care or understand digital, so what it will see is the whole average. However, if that signal is provided to the LED in a rate or a frequency, let's call it FWM, okay, PWM basically, the frequency of the pulse width modulation or the period of the pulse width modulation, PWM. If it is too slow, for example, let's say we set it up to be a 10 hertz signal, as it turns out that this LED would appear as if it's flickering because it might, even though you have set it up to the correct percentage or correct duty cycle, it might appear very flickering. And similarly, if you actually change this to 10 megahertz, for example, it might be too fast for that particular LED to turn on and off, and it will actually not show you the effect that you're after. And again, similarly, this particular frequency or this particular signal might not be connected to an LED but to a motor. So these two frequencies also might be too fast or too slow. And motors generally are in the few kilohertz to 10 kilohertz depending on the voltage they operate at and depending on the type of motor, whether it's a servo or some other type of motor like a DC motor. So we do need to, in addition to the duty cycle, we do need to pay attention to the switching frequency whenever we're going to design that particular circuit. The next thing we need to worry about or actually figure out is the resolution. And the resolution is actually just the granularity of which the duty cycle change. So the duty cycle, which we call D, is just a number that goes from 0 all the way to 1, 1 being 100% in the on position. So mathematically speaking or theoretically speaking, it's just a real number between 0 and 1, and there are infinite numbers that we can have. So you can have 0 point, for example, 1, 2, 3, 4, 5, whatever number you have. However, we're designing a digital circuit, so this does not work. We can't have infinite numbers. We have to have a certain number of numbers. And that is usually specified by the resolution. And generally speaking, in digital logic, what affects that is actually number of bits. We're going to call it R. So if you have R, that means you have 2 to the power R levels or numbers between 0 and 1 that you can actually utilize. And the difference between them is actually 1 divided by 2 to the power R. So let me give you an example. So the example in here that I'm showing you is if R is 8 bits, let's just specify that R is 8 bits. That means you have 256 levels total. 256, that goes basically between 0 to 1, you have 256 levels. So if you take a look at that number here, so we're going to start by 0 divided by 256. This is actually my 0D, and this one here is my 1D, which is the very last one. And of course, any level in between them is just a number, and I have 256. Some of you might think about it, well, this is 256, not 255. That's not an error, and we're going to account for it later. But for now, you just need to know that I have a certain resolution. So in addition to the duty cycle, we need to figure out what the switching frequency is because different devices, different analog devices expect different frequencies, and what is the resolution of my system. Okay, so let's jump into a very basic design for a circuit that generates pulse width modulation signals. The general design or the most basic design is actually a design that has mainly two components. The first component, which is here, is just a counter, just a normal binary counter that operates whatever the system frequency is in here. Okay, provided with that particular clock, and it just always adding 1, 2, 3, 4, and it just rotates. And I called it an R bit, and this is actually the same R that we talked about in terms of resolution. So this design actually does account for R for the resolution. Okay, so it can go from 0, 1, 2, 3, and whatever the output of this here, we'll just call it D_reg. What we will do is we'll provide it with some sort of an input. This is the duty cycle that I care about. And the second component of this design after the register is just the comparator. So the comparator compares the value that is outputted from the register in the duty cycle. So if the value of the D register is less than the duty cycle, it will output 1. Okay, so what it will do is basically will stay 1, 1, 1, 1, 1 until you figure out the duty the value D. And then at that particular moment, the comparator, what it would do is actually will just give you a 0. And it repeats. Then you go in here and then the counter finishes. So basically the counter here, this particular counter is at 0. Okay, and it finishes in here to 2 to the power R, for example, -1. That's what it has, because it has R bits. This is actually in here. So what it does, then it goes in and it does the same exact thing depending on the value of duty. So the value that it does in here is actually D -1. Okay, so from 0 all the way to D -1, it's actually the duty, and that's how it operates. It's pretty straightforward. So a couple of components, a counter followed by a comparator. So in here we have provided, we can utilize a D flip-flop, and the reason why is we want to avoid any glitches. Sometimes you might have some signal in here and signal in here, and a glitch would be something like a one that is super short and it's outside my specs. And the reason why we might have this is because the comparator itself is actually is actually a combinational circuit, and it can change at any moment. So if the register itself is changing certain bits internally, it might like one of the bits is changing while the other, like basically it's changing the bits, but not all of the bits change at the same time, and maybe one of the bits within its own internal register changes faster than the others. It might create a situation where the duty cycle is actually larger, and it will just output some glitches in here. So to avoid all of this, I will wait for the comparator to finish, and I'll just delay it by some sort of a delay for using some sort of a D flip-flop here. Okay, and that D flip-flop it's a single D flip-flop and its purpose to avoid these glitches. So let's see the implementation in Verilog. The implementation in Verilog is very straightforward. You can read it. What you need to pay attention to is we have a parameter called R, and the R actually controls the duty here. Basically, the input duty is actually an R bit in here. Okay, and what we have in here is we have a register, and that register in here, the D register, is actually also R bit. This is what we have. We have this to be R bits. Okay, and then this is just straightforward in here. So we see that the register is always incrementing no matter what. It's just always incrementing. However, the pulse width modulation signal, it's actually based on whether that D register and the duty. It's just basically compare them. And of course, because we are using this particular register, this is what the PWM next is, and you'll see the PWM out. It's just basically the registered output, and that's it. It's pretty straightforward.